Hi, it's Professor Cummings, and I am here to go through the homework problems that you guys had turned in last week. I wanted to work through those and kind of just walk through the logic as well as give you guys the answers that you'll be able to take down and use as a study guide. So let's go ahead and go through the problems here. Alrighty, so here we had three problems. Okay, one was a compound gear train. The other two were planetary gear trains, and they all had the same input motor of 3,600 RPM and 26 foot-pounds of torque. For problem number one, you had to calculate the train value, the output speed, and the output torque. And for problems number 2 and 3, you had to calculate the output speed, the output torque at the highest overdrive. And for, let's see, number 3, again, output speed and output torque. So let's walk through these. Okay, starting with the first one. But first, let's look at the velocity ratio, and let's go over this concept first, because that's going to be important for that, for all the problems, but particularly for the first one with the compound gear train. Just velocity ratio is the ratio of the rotational speed of the input gear to that of the output gear for any single pair of gears. So we're looking at this in terms of the teeth. You've got the driven and the driver. So the velocity ratio is the ratio of the driven over the driver gear. So it's just a multiplier. So when we look at this, we've got two gears in a gear train, or two gears together. One is 25 teeth and one is 75 teeth. The driver has 25 and the driven has 75 teeth. So if we look at the velocity ratio, it's 75 to 25, or 3. And that 3 is going to be the multiplier for knowing what the input and output, how much the speed changes or how much the torque changes. And when we think about train value, we're looking at the same concept. It's a multiplier, but now we're looking at a whole gear train, not just two gears, a pair of gearing. So let's look at how this works out. So if you got the first pair of gear, with an input shaft, and then you got the second pair of gear which are connected, that is actually a compound gear train. So the train value is just the ratio of the input speed, so what's going on the gear going in, to the output speed, the last gear in the gear train. Another way of looking at it, it is the product of the velocity ratios of the gears. So the ratio of the first set and the ratio of the second set multiplied together gives you the train value. So you need to know both the velocity ratios to get the train value. So let's work on this first problem here. So we've got a compound gear train, and you can see the input going into gear number 1 and the output going out of gear number 2, or it's gear number 4. The first gear is 16 teeth. The second gear is 32 teeth, third gear is 18 teeth, and the fourth gear is 36 teeth. And again, we're trying to calculate the train value, the output speed, and the output torque. So here we have a velocity ratio based around the teeth, the number of teeth on the driven gear versus the number of teeth on the driver gear. So again, that is the driven gear for the first set is 32. Or driven gear is 32, and for the driven gear, driver gear, it's 16 teeth, gear number 1. So that gives us a velocity ratio of 2. For the second set, again, the driven gear is 36 teeth, that's gear number 4, and the driver gear is 18 teeth, that's gear number 3. So we got a velocity ratio of 2. And the train value is the product of that, which is 4. So we've got a velocity ratio of 2 for the first, 2 for the second, and a total train value of 4. So that's going to be our multiplier. So when we look at what the output speed is. We need to know what that train value is for that 3600 RPM input and that 26 foot-pounds of torque, multiplied by the train value. We can see the torque is 104 foot-pounds, and the output speed, 3600 over 4, comes out to 900 RPM. And in this case, it's going counterclockwise. So that's problem number 1. Now, before we go into the other 2 problems, those are a planetary gearing problem. And I want you to remember there are 5 laws of planetary gearing. And there's one that we're going to be looking at, and it's this overdrive condition. And that's because the carrier is the input. Okay, and that's what we're being asked on number 2, is we weren't being told to find the maximum overdrive, the highest amount of overdrive. And that's the carrier as the input. And that's what we know is going in. So that means that motor is directly tied to the carrier. So let's see how we're going to figure that out. So we're being asked for the highest overdrive. Now, when you think of the highest overdrive, there are 2 possible conditions. And 2 possible conditions, and with the carrier as the input at 3600 RPM, that's our given. The first one is that the ring can be the output. And the second one is the sun gear can be the output. All right, so we got 2 possible ways we can go into overdrive, and one is going to be higher than the other, but both are going to take this from 3600 to something higher than 3600 RPM. So let's see what we can do about that. We're going to figure out what we're going to do is we're going to look at both conditions. So here's what we're given. We've got a ring gear of 36 teeth. We've got a sun gear with 16 teeth. And we're being asked to calculate the output speed and the output torque at the highest overdrive. All right. So again, remember that the carrier is the input in both conditions. And we've got the output as the ring and the sun is stationary. So that's going to be one scenario. Just assuming that the ring is an output. So let's see. We were told to use the tabular method. So here's your table. We calculated this before, but the row I want you to be careful to pay attention to, I've got highlighted, is the total motion. And the way this table is set up, you can see that the carrier is by Y. So that's the value of the carrier rotation. The sun gear rotation is by this equation, X plus Y. And the ring gear's rotation is going to be calculated by Y minus X times the ratio of the sun and the ring, based on the number of teeth. Okay, so we've got these 3 equations that we're going to work with, and we've got a value of Y is 3600. So we know that. We also know that the sun in this scenario, sun gear is stationary, so we know a value for that. That equals 0. So what we really are trying to find out is what this output speed of the ring gear. So let's go here. We got a value of the carrier at 3600 RPM. We've got an equation that gives us the value of the sun gear. X plus Y is 0. So we just subtract X from both sides, and Y is equal to negative X. Okay, that's as far as we can take that. And then we've got Y minus X, and the ratio of the sun to ring is equal to whatever that output velocity is going to be. Okay, so here's what we have. We've got 2 equations and 2 unknowns. But we can do a substitution. We do know the value of Y in this equation. We also know that Y is equal to negative X. So we'll substitute this. So we will substitute that as 3600 minus, and since Y is a negative X, negative 3600. And there's 16 teeth in the sun gear and 36 teeth in the ring gear. And that's going to be the value of the output. And that works out to 5200 RPM, which is what we should expect in an overdrive condition, the carrier as the input. All right, now let's see, we've also got to figure out what the torque is. So we've got a velocity ratio of the output versus the input. So we need that multiplier, and we do know those. We got the output of 5,200, the input of 3,600. So our velocity ratio is 1.4. So we know our torque is going to also be a product of that multiplier. So 26 divided by 1.4 means that we go to 18 foot-pounds of torque, which is again what you would expect in an overdrive condition. You gain in RPM, but you go down in torque. So now let's look at the second condition. This is where the ring is the output. Let's see what happens when we make the sun the output. Again, same table. That didn't change at all. Same three equations. The carrier is Y, the sun gear is X plus Y, the ring gear is Y minus X, and the ratio of the sun and the ring in terms of teeth. And the input is still the carrier, still 3,600 RPM, still going to get our overdrive condition. All right, so now let's work through this. Again, Y is still 3,600. We know our ring is stationary in this condition, so that equals 0. It's not moving. So Y minus X and the ratio of sun to ring. Now we can add that ratio of sun to ring times X to both sides of the equation and get a value for Y, or have Y equal to X times number of teeth in the sun divided by the number of teeth in the ring. Now we've got substitute for these values, and we have 3,600, which we do know for Y, and that ratio comes out to 0.44 times X. We can get a value for X. 8181. All right. So now we've got to look at what the sun is doing, because we never used that equation yet. So X plus Y is our output. Now, since we know X is 8181, we know Y is 3,600. Our output is 11,781 RPMs. So we can find our velocity ratio, which is output over our input. 11,781 to 3,600. So our velocity ratio is 3.27. All right. So our output torque is going to be 7.9 foot-pounds. So our torque goes down from 26 to 7.9, but our velocity goes from 3,600 to 11,781. So what we can see is for question number 2, the highest overdrive is going to be when we use the sun as the output and keep the ring stationary. So what we have is an input on the carrier at 3,600, 26 foot-pounds of torque. We'll have an output of 11,781 RPM, and our torque will go down to 7.9, and that'll be our velocity ratio. Now let's look at this one. Number 3 is an interesting one. Okay, because we have, planetary gear, got the same inputs as number 2, as far as the motor goes, 3,600 RPM, 26 foot-pounds of torque. Our input is our sun, and our output is our carrier. All right, so that means 3,600 RPM is going to be the sun. We've got an output of the carrier that we don't know what that's going to be, but here's the twist. We've got a ring gear going at 1,000 RPM counterclockwise. Now, direction is going to be more important in this one than in the others. So we got our direction, rotation, or sign convention is counterclockwise is positive. And we've got our ring gear going counterclockwise. So our ring gear and our sun gear are going in opposite directions. So the real question is what's going on with that carrier? So the ring gear is going at 1,000 RPM, clockwise, or we could say it's negative. our sun gear is going at 3600 RPM counterclockwise. And so we've got to know both what is the direction of that carrier as well as what speed is it taking on. All right. Under normal conditions, this would be an underdrive condition, but that may or may not be the case when you have motion on that ring, because those 5 rules also assume that certain gearing are stationary. So since that's not the case, we're going to have to consider what the tooth speed is on both of those, which is totally different from RPM. So let's look at this. We can still use our tabular method. So our equations are still valid, but now we've got to consider there are going to be completely different values for these, as well as neither one of these equations or any of these equations are going to go to 0. They all have a value to them now. So it's just a matter of finding out what they are, particularly because we don't know what the carrier, that's the output. We don't know what that's going to be. So let's start with our sun, which is x plus y. Since that's the input, we know that's 3600 RPM. So we will put that in terms of y, of what the carrier is doing. So it's 3600 minus x is going to be our value of our carrier, whatever that happens to be. Now, if we look at what the ring gear is doing, we'll have to use this equation, and we know what its value is. It's going at 1000 RPM clockwise or negative. All right, so y minus x times the ratio of the sun to the ring in terms of its teeth is equal to negative 1000 RPM. So again, now we've got 2 equations, 2 unknown. So we can substitute this value of y, 3600 minus x, 3600 minus x for y in this equation. We've got this ratio of sun to ring, 0.44, times x is equal to a negative 1000. So what we can do is we can add 1000 to both sides. That's 4600. And we can add these two together, end up with 1.44x, and add that to both sides. And we get 4600 is equal to 1.44 times x. And now we just solve for x. So x is 3194.4. All right, so now we've got a value for x, and now we can start solving for y, which is our output, our carrier. So we substitute for x, we get 3600 minus 3194.4, and we end up with the value of the carrier as 405.6 RPM going counterclockwise. So it's still going in the positive direction, going counterclockwise. And what we can see is that the motion of the ring, opposing it, has slowed it down. Slowed it down pretty dramatically. So let's figure out what the velocity ratio is. So it's the output versus the input, or 0.11. So that means, you're actually stepping down in your RPM. So we can figure out now, using that same multiplier, the velocity ratio, to figure out what the torque's going to do. So we can see that since the torque went down dramatically, we expect the torque to go up dramatically. So we go from 26 foot-pounds to 231 foot-pounds of torque. So that's the influence of having motion on your ring gear when you've got an input on your sun gear and you're using your carrier as your output. So you can see that as a way of actually getting a lot of variation, on an output without actually doing a whole lot of change-ups. You just got to control the variable on that one particular part of your planetary gearing system. And we've done an example in class where we actually took this system and made it go into reverse. So that is your answers for your homework assignment, and I'll get back to you soon.